Welcome to Econ 317. In this instruction video, we will go over a problem of finding solutions to situations where we have two equations and two unknowns, or in general, n equations and n unknowns. So let's first write it down. So two equations, two unknowns. For example, 2x plus 3y equal to 2, 4x plus y equal to 5. So this is equation number 1, this is equation number 2, and two unknowns are x and y. Notice x and y appear in linear form, so both are raised to the power 1. That's how we will call this system of equations to be linear equations. Any solution we find, values of x and y must satisfy each one of these two equations simultaneously. I could write a general case n equations and n unknowns. So in this situation, we will instead of writing x and y as the unknowns, maybe I will use a more general notation. Unknowns are x1 subscript 1 for x, x2 subscript 2 for x. I go on and on. I write subscript n for x. And then we need to write down now n equations. Again, we will have to have a general notation. So let me write it this way. For the first equation, I will have a11 times x1. So this is the coefficient of variable x1. I go to the next one, a12 for variable x2, on and on, a1n, xn, and then we have a constant on the right hand side. I will write it as b1. So this is our equation 1, but now you can see it is a general form. I can go on and write the remaining n minus 1 equations. So I'll write down at least one more. So now this is the second equation. I'll make the coefficient read a21 x1. I go on and on. I write 2n xn, and then I have on the right hand side b2. Notice I have followed a consistent pattern in the sense that every time I write an equation, I will write each one of the variables in identical order. So x1 precedes x2, x2 precedes x3, on and on. I have already written the second equation. Let me go ahead and now write down the last one, an1 x1, an2 x2. I go on ann xn, and it is equal to bn. Remember, b1, b2, bn are all constant, and there are equations in the middle. So this will be a general case of n equations with n unknowns. Usually, whenever we come across such situations, for example, two equations, two unknowns, we are able to solve them for particular values of x and y. In this video, we will like to look at what are the conditions required for those two equations to be matched, to be met, so that we are able to find a solution. Or in other words, when I say solution, we will like to know under what circumstance these equations generate a unique solution. So conditions required for a unique solution. I start with examples just to show that it is not always the case that we will have a unique solution. So let me write down an example of two equations, two unknowns. I have 2x plus 3y equal to 2. That's my equation number 1. Two unknowns x and y. 2x plus 3y equal to 5, equation number 2. And you can see there is a problem. There is a problem in the sense that in the first equation, in both the equations, the left hand side is same, 2x plus 3y. Left hand side is same, but you notice the right hand side is 2 for equation number 1 and 5 for equation number 2. So it cannot be possible for any value of x and y such that 2x plus 3y equals 2 as well as simultaneously also equals 5. So this set of equations will have no solution. And we will give this situation a name. We will call these two equations are not consistent. These equations are inconsistent, and which means there will not be any solution. So inconsistent, that's a problem. We will like to avoid such situation. And next we have one more situation where it may not be possible for us to get, it will not be possible for us to get a unique solution, and that's the one I am going to explain now. So I continue with the first equation I wrote before. So 2x plus 3y equal to 2, that was our equation number 1. Now let me write this second equation, 4x plus 3y equal to 4. Now you can see the second equation is somehow related to the first one, in the sense that if I multiply the first equation by 2, I am able to get the second equation. Right, left hand side is exactly 2 times the first equation. Left hand side of equation 2 is exactly 2 times the left hand side of equation 1, and similarly on the right hand side. So in this situation also, we will not be able to get a unique solution. We will say equation 2 is functionally dependent on equation 1. And I explained precisely in what sense. Second equation is twice the first equation, and again we will not have a unique solution. We can try. Let's say I will at least show more than one solution so that we know why uniqueness is not guaranteed. So let's take x equal to 0, y equal to 2/3. That's a solution which will satisfy both these equations. And then I take x equal to 1, y equal to 0. Again, this is a solution which will satisfy both the equations. And so we are we are not able to obtain the unique solution. So in order for us to have a unique solution for two equations, two unknown, or more in general, n equations, n unknowns, what we require is the system of linear simultaneous equation must satisfy two conditions. They are consistent so there is no contradiction in the sense of one equation being satisfied does not preclude the other equation to be satisfied. And second, we have functional independence. We will also call it not redundant. It should not be the case that one of the equations can be obtained from the second equation by multiplying a common factor. If we have this situation, then we will be able to get a unique solution for the system of equations. So let's have an example where we indeed are able to get a unique solution. So my first equation, 2x plus 3y equal to 7. I will give example for only two equations, two unknowns. And then the second equation is 3x plus 2y equal to 8. We can notice that these two equations are consistent in the sense that it is not possible to come to a situation where one set of numerical values assigned to x and y satisfying equation 1 does not preclude the second equation to be satisfied for the same value. That's the consistency. And then these two equations are functionally independent in the sense that one cannot obtain the first equation by multiplying the second by any common factor. So here we will indeed have a unique solution. And I will spend some time to figure out this unique solution. There are many ways to solve for the solution of two equations, two unknowns. As we go into larger and larger number of equations and equal number of unknowns, typically we would use some computational facility like most of the calculators, the graphing calculators, they are able to solve these type of equations, or maybe we will use some computing power. So here what I am going to do is I will multiply the first equation by 3 and the second equation by 8 to obtain the transformed first equation turns out to be 6x plus 9y equal to 21. Then the second equation multiplied by 2 turns out to be 6x plus 4y equal to 16. And now you can see why I did this type of multiplication, because what we have obtained now is both these equations have the first term equal to 6x. So now I can subtract the second equation from the first one, which leads to the first term being cancelled out. 9y minus 4y is 5y. And on the right hand side we have 21 minus 16 equal to 5. I can divide both sides by 5 because I need y by itself on the left hand side, and I get y equal to 1. Once I have obtained the value of y, we can plug it in any one of the two equations, and we will be able to get the value of x. So let's do this. 2x plus 3 times 1 equal to 7. 2x plus 3 equal to 7. I subtract 3 from both sides. What obtains on the left hand side is 2x by itself, and 7 minus 3, 4 on the right hand side. I divide both sides by 2, and then we obtain x equal to 2. So x equal to 2, y equal to 1 is the unique solution, because these two equations were consistent or were not inconsistent and are functionally independent. So is the unique solution. And this is a good point to stop.